Hello, welcome to this presentation. This is going to be, topic is things I learned managing 250 gigabytes PostgreSQL database. So let's start. This is how the idea for this brown bag started. I had been working on a project for almost a year and a half, and for some time on the project, we had a database around 300 gigabytes in size. Now it's around 125 gigabytes. When I joined, the client paid almost $2,000 for 2 instances of Microsoft SQL Server. We had a lot of issues with slow queries and requests timing out. Any change in the database took ages. For example, creating new columns on tables or changing indexes. So what can you do when you have similar issues? You can just throw more money on it. I guess $4,000 would make it better. But that was not an option for our client. He actually wanted to save some money. And we were tired of working with the slow database without many options to improve it. The SQL Server really was pricey, and we weren't the main maintainers of the database. We mostly just used the data and with few tweaks here and there, but that was it. So what are other options we have? We could probably also not use the managed database, maybe even leave the cloud to get some cheaper services, but we were a really small team without a dedicated full-time DevOps guy, and setting up everything would be quite costly, and management and updates would also cost some time and money. So that was not an option for us either. But to be honest, I have less downtime on my $5 server in Germany than we had in Azure, so it could be fun. And last option I want to talk about is optimization of database. The older I get, the more I like the stable and boring world of SQL databases, unlike the Node.js ecosystem. I started working with PostgreSQL 13 years ago in my previous job. They were really great database specialists, but I wasn't really into it back then, and I was happy to offload any database task to them. But it's different now, and I'm really looking forward to challenges like this. So back to the topic. Shortly after I joined the project, PostgreSQL version 13 was announced with one very useful feature that really made a difference for us. I'll get back to that later. I knew this could be a good opportunity to save some money for the client in the long run, and it would drastically improve performance of the application. So fast forward today, the client pays around $50 per month for 2 instances of PostgreSQL, and still in the cloud, and the performance is really day and night. To show you the journey, I've prepared an example database we're going to optimize today. So this is the database. It's all about cats. Each cat has an ID, name, and owner. Each owner has a name. We have 5,000 owners. Each owner has 20 cats. That's 100,000 cats in total. A lot of numbers, sorry. There's one last table for tracking how many things does each cat drop every day. It tracks data from 2018 to 2021, so 4 years. The issue is that the table has more than 7 gigabytes for 146 million rows. And the main index, which is used for searching in the table, has over 5 gigabytes. This is probably the worst case you can get, so let's optimize it. By the way, at first I wanted to surprise you. At the end, how much data we were able to save, but because there are not just developers watching this presentation, and next several slides could be boring for some people, so in case you doze off, we'll reduce the size of database by almost 12 gigabytes. So let's get to it. So here you can see some sample data. This is what we already have, that 5 gigabyte for unique index. Unique index can guarantee us uniqueness, of course, and it can quickly find a specific row. So row for a single cat on a single day. It would be fast if it wouldn't have 5 gigabytes on a machine with 4 gigs of RAM. So when the index is not fully loaded into memory, we pay the price for another extra step, reading the index data from disk. The first thing how we can try to improve this is to reduce the amount of data we store in the index. So let's see how it looks when we drop that unique index and create new one with only the cat ID in it. Indexing only the first column, cat ID, definitely reduces the amount of data we need to store in the index. Now we don't have to store the date, but we still have to store the big UID. The size went down to 4 gigabytes. The issue is that the index is no longer pointing to a specific row. So each cat in the index actually points, each cat ID in the index actually points to 1461 rows, because we have 4 years of data. That's 365 days times 4 rows plus 1 leap year. So when you search for data for a specific cat on a specific day, you have to fetch those 1461 rows from the database and then filter out, this is using the index, and then filter out the 1460 rows you're not interested in. So you'll end up with just the 1 row you wanted. In reality, this could be even worse than the previous unique index. So what can we do next? We can just upgrade PostgreSQL to version 13. This version has a new feature called index deduplication. That means it stores each value in the index only once. It still stores all pointers to the rows with duplicate ID, but it stores that big UID, that 00004C69 value, only once. This simple step reduced our index from 4 gigabytes to just 1 gigabyte. By the way, you can't do that with the unique index because there's nothing to be duplicated. This was actually our starting point when we migrated on the project from SQL Server to Postgres. And it was the reason why we migrated. It roughly cut size of our indexes 4 to 6 times. It was a huge leap for us, but this was just the beginning. If you feel lucky, you can try to guess how small the smallest index is going to be today. In this example, I know I made it easier for you when I mentioned how much we'll reduce the size of the whole database. And no, it's not a trick question. It won't be 0. So if you feel especially lucky today, you can send your guess to Slido along with some question. And now quiz time. What happens when you run this query? Simple answer is that it will find 1 row for us, data for 1 cat on 1 day, and return it. That's true, but there's a lot of stuff you don't see. First of all, the query doesn't only fetch 1 row from the disk, it fetches roughly 160 rows from the disk. Why? PostgreSQL, for PostgreSQL, the smallest unit of disk read-write operation is a page. They call it a page. And a page has 8 kilobytes. It does not matter if you only want 1 row, Postgres will always fetch the whole 8 kilobyte page. It also doesn't matter if you only want to update 1 row, it will again save the whole page. This is how the page looks like. It has a header. There are pointers to rows stored from the beginning of the page. Actual row data are stored from the end of the page. When they meet somewhere in the middle, that means the page is full. By the way, you can control how full should the page be. For example, if you have a table with a lot of updates, making the table less full will increase your chances of storing updated row in the same page, which is more efficient than storing it somewhere else. That's because each row actually exists in multiple copies, one for each transaction. If you store a new version of the row on different page, you actually need to save two 8KB pages, one for the old version that you change and one for the new version. So it's also more efficient to update indexes when a new version of the row ends up on the same page. Another quiz time. What happens when you run this query? So with knowledge from the previous quiz time, you probably know it's all about pages, because in this example, the data are sorted by the date. That means each one of the 1461 rows for a single cat, so 4 years of data, could be and is actually stored on a different page. So we can't just load 1461 rows. We have to load 1461 pages. That's 11 megabytes of data for a single cat. And for all cats of a single owner, who has 20 cats, by the way, that's almost 230 megabytes of data. But if we sort the data in the table, so all the rows for a single cat would be stored next to each other, like this. So it's sorted by the cat, and you get all the dates next to each other. This way, we would only need to fetch 1.5 megabyte. So that's a big difference. We can use it in next slide. So let's get to it. Previously, I used B3 index. That's one of the most common and most versatile. They are great for fetching small amount of data real fast. B3 indexes have their index deduplication feature I mentioned. It helped reduce size of the index a lot in previous step. Here we can use gin index. It's a different type of index. It has also one cool feature. It is more size efficient when the values for a single ID are stored next to each other. So when you sort the data by cat ID, that's when you get a smaller index. So by just presorting the table by cat ID, we get gin index less than 200 megabytes in size. Cool, right? With the sorting, without the sorting, it would go over 1 gigabyte. So it would be comparable with previous B3 index we had in previous step. So we got reduction by 80% just because of different sorting of the data in the table. By the way, gin index is in general smaller than B3, so it probably wouldn't be a good idea to use that 1 gigabyte index without resorting the data. We already reduced the size of the index 25 times, but the size of the table means we still could have some slow queries, so let's focus on that for a moment. I've created a new table for this step. Please notice that last column, it's no longer a number, but an array of numbers, and the date no longer shows each individual day, but only the first day of the month. Yes, the data are aggregated. Instead of daily rows, we have one row for a whole month. Position of the number in the array of dropped things corresponds to a day in a month. So first value 7th of January. First value 7 is 1st of January. Second value again 7 is January the 2nd, and third value in the array is January the 3rd. So there's 28 to 31 values in the array. Thanks to this change, the size of the table went down from more than 7 gigabytes to slightly over 600 megabytes, but we still store the same amount of information. What's important here you can't actually see is that besides those 3 columns, each row has actually a header data. PostgreSQL stores mostly transaction data in it, and it has around 23 bytes. That accounts for roughly half the size of the original table. So by aggregating the data, we also get rid of these headers. So remember, each row has an overhead. Reducing number of rows also reduces amount of information we get we need to store in an index. So for the GIN index, we're down to 16 megabytes, and for the B3 index, which would probably be faster for most cases, we got 33 megabytes. That's a great achievement, and to be honest, I would be happy with that. But let's try one more improvement, another type of index. And that's BRIN index. BRIN stands for block range index. While GIN index benefited from pre-sorted table and it was able to compress the index this way, BRIN index actually requires the data to be pre-sorted. It doesn't store pointers to actual rows like the previous B3 and GIN index, but it stores minimum and maximum value in a block of pages. That means the index is quite lossy. Thanks to that, we ended up with really tiny index. It has less than 100 kilobytes. BRIN index is great for indexing foreign keys with the low cardinality. That means the value doesn't repeat. Well, the value does repeat often. Or for time series data, or even for auto-documented primary keys, but unfortunately, it can't guarantee uniqueness. In the simplified example here on the image, there's a table with data stored across 15 pages. When we create a BRIN index with 5 pages per block, we'll end up with just 3 ranges in the index. Each range, each record in the index stores minimum and maximum value of the block of pages. Here you can see why it requires pre-sorted data. It's like a contact list on your phone. So if you search for a person named John, for example, you know it's in the second block between characters E and S. Even if you search for a single row, you'll always end up loading those 5 pages from the disk. Postgres then goes through all the rows again in the whole block of pages and filters out the ones you don't want. So there's an overhead of that double filtering, but the first search by an index is pretty fast, even if you want thousands of rows. So that's what we got. The index went down from 5.1 gigabytes to 96 kilobytes while still being fast. And it really depends what type of queries you want to run. So don't take this as a rule of thumb, but really test your indexes. And also, it's not all about the indexes. Sometimes also making the table smaller might bring a lot of improvements in performance. So yeah, you can also try that. That's all from my side. I have a few more tips how you can optimize your database, potentially reducing sizes of tables by tens of % in some specific conditions. But that would be too much for a single presentation. So thanks for listening. And now let's see if we have some questions in Slido.